Hi, today I'm going to be showing you a good way to visualize the chirality and how the stereochemistry is determined in the Keck asymmetric allylation reaction. The Keck allylation reaction involves the nucleophilic addition of an allyl group to an aldehyde. The stereochemistry of the product is determined by a chiral complex of a titanium binyl group. The binyl group is used as a ligand attached to the titanium. So binyl group is interesting in that it is very chiral. As you can see here, this is a model of one. So we have one set of aromatic rings that's in the plane, and then another essentially coming out or behind, depending on which way you look at it. Now this is hard to model using marshmallows and toothpicks, and it's definitely not expected that everyone does that, but a good way to use that is just using paper to demonstrate this instead. So to start the visualization of the reaction, we have to make the tetrahedral center of the titanium. So if you can't visualize a tetrahedral center, which a lot of people can't, one of the easiest ways to do this is using marshmallows and toothpicks. So here I have one marshmallow and 4 toothpicks. And to make it, again, tetrahedral has 3 in the plane and then 1 coming out of the plane. 1 bond coming out of the plane. Just like that. So here's our tetrahedral center. This is really easy to make. Again, you can look at it from multiple directions. It's always tetrahedral. From this group, we can add our binyl groups to visualize where our allyl group is going to attack. Again, if we look at the binyl made out of marshmallows and toothpicks here, we can see that when it is added, there would be oxygens as well, but this will add somewhere that'll look like right here. So we've got one group coming out or going back depending on how you look at it, and it forms a ring right in here with oxygens connecting this bond to the carbons. I'm going to set our tetrahedral center. In this case it is going to be titanium for this reaction, so I might refer to it as that. I'm going to set it aside and show you how to make an example of a binyl complex. So I just have this piece of paper here. I'm going to use blue so that it stands out better, but you can use whatever you want. If you just cut your paper into smaller sizes so it's easier to work with, you could leave it big, but it can be hard to see. So the main idea of the binyl groups is that one group goes up in the plane, one group comes out of the plane. So to do this, we can just cut our paper almost to the edge, but not all the way, and fold one side up, like this. Now in reality, there would be a little bit going back this way as well. However, to show the chirality, this works just fine. So I'm going to do that one more time. And now we have our 2 binyl groups. This just shows the way that they are laid out. And here's an example of the paper next to the molecular diagram. So you can see they both kind of come out this way with the bottom part in the plane. So bringing our tetrahedral center back, here we have it. We're going to look at how this plays into where the nucleophilic attack is going to occur. So in this case we have an aldehyde. I have a model of the aldehyde here. You can also just picture it in your head. Here's where the tetrahedral center comes into play. So in this reaction in the complex that we're trying to form, one of our in-plane tetrahedral bonds is bound to an oxygen, which is part of our aldehyde group. So in this case, I've got our oxygen here double bonded to the carbon, and then this is our R group with a hydrogen. I made a model of it. Again, if you can either picture it, or if you have one model, if you're doing this in a big group, you can have one model and just go around and show people where it would go. Now for the placement of our binyl groups. So this is the part that's important because this is what determines where the attack comes from. So when we set these down, if you look at the catalyst binding model that we're trying to form here. Here is the drawing that you can look at. We have 2 of them in the plane, so this one's just going to go right here. These 2 bonds are in the plane. As you can see, we've got one binyl group coming out, one in the plane. Alright, for the second group, the interesting part is that it comes off of the bond that's coming out of the page in our tertiary model. So when we have our vinyl group, what's going to happen is this is going to bond to the top. Oh, this is a little bit too long. And our vinyl group is going to be going down, covering our aldehyde. This essentially makes a kind of a pocket that you can see in here where the aldehyde is. So again, we have our other vinyl group right here. If we place it on top, this is what it's going to look like, and this is how the bonds are formed. So it's kind of hard to see here, but we do have this pocket going in here. This shows it is very sterically hindered on this side. These vinyl groups are huge. This paper group is not exactly to scale in that way, but the vinyl groups are very, very big. So what this means is that when we have our nucleophilic attack, there's no way that it's going to come from this side. So if we look at our nucleophile here, so here's what our group with the two vinyls looks like. As you can see, it's super sterically hindered from the top. This is a really good visual model because you can see this hindrance both from right here, this group coming out of the page, as well as this group that's essentially blocking the whole aldehyde. So when we have our alkyl group here, it's not going to be able to attack from this side. It doesn't fit. So what's going to happen is it has to come from the back. And when it comes from the back and attacks our, I'm going to remove this vinyl so it's easier to see. When it comes from the bottom and attacks our carbon center here, what it's going to do is it's going to push this oxygen forward because it has room to go into essentially a little pocket. So again, this is going to come from the bottom and push our oxygen towards us into this little pocket in here. Removing our vinyl groups, we can see that it's a lot easier for our allyl group to attack from the bottom. Essentially what the vinyls did was create a bowl over this entire section of the reaction, meaning that this group here could not fit going this way. That vinyl group was just way too large and way too chiral. So what we have instead is a group that attacks from the bottom. And so that makes it easier for this group to come in underneath, attack here, right here, forming a bond there, which leads to our oxygen pushing forward into that bowl that was created by the vinyls.
So when we look at what we just demonstrated physically, it's easy to see how this plays into the attack side and the resulting stereochemistry of our product. So we saw that our vinyls, which on this mechanism are here, here, and here, attached to our titanium, they essentially make a bowl over this oxygen, something like this. From this, it was easy to see that our nucleophilic attack would happen from the back, not the front, because it was too sterically hindered. This resulted in our oxygen being pushed forward, which is exactly what we see here in the mechanism. This is an absolute stereochemistry that occurs from this reaction because of this blockage that we see by the vinyl groups. And if you follow the mechanism through, you can see here that our product is indeed a frontal oxygen.